Okay. So we are discussing about audio event detection or sound event detection. Oh. Just a moment. Yeah, so we are discussing about sound event detection and we are discussing this paper. How many of you have started reading this paper? Okay, at least two of you. Sorry. It's a very good paper. It will connect your base theory with the practice. Most of the concepts or most of the theory which is discussed in the paper, the mathematics of it or the basics of it are already known to you. We have discussed in this course. And some things which we have not discussed are the applications of those concepts for this particular problem. That is what we want to do through this paper. We discussed about cocktail party effect and yeah. So we discussed about polyphony as well, right? What is polyphony? Polyphony means you have multiple sound sources playing together. Like I'm speaking and this AC sound is there in the background. Of course, when I speak, at that time, my spoken energy is more in this case, or the energy in my speech is more compared to the energy in the audio, this air-conditioned sound. But there could also be cases when my intensity and the other source's intensity are almost similar. But then still people are able to make out what I'm saying. Right? Let's say two people are speaking, you can still focus on somebody's voice. And then we discuss number of possible classes could be unlimited, right? Let's say you made a system to detect only AC sound, but then the fan also is running. And then you deployed your system in a place where there are some other kind of sounds also present. So how many sounds can you train your system for? So the number of possible classes is unlimited. That's why any ideas how do we deal with this problem then? How do we kind of categorize them, or how do we make a representation if the number of possible classes is unlimited? But you don't know what to focus on. This class में AC भी है, पंखा भी है. There is also somebody speaking. There is also dog comes sometimes. There is sometimes somebody steps into the room, so there is walking steps. Somebody is coughing, somebody is sneezing. All those sounds are there. How many categories can you make? And there is no specific sound to focus on. You have to kind of tell all the possible sounds present in the room. So
every unique kind of sound is just classified into one different bucket.
Yeah. So basically, one possible approach could be don't call them as categories, but give a continuous representation, and then depending on where they lie in the space, you can give it a name. Right? For example, if you make a continuous space, right? Don't make discrete buckets, make continuous space, and in this space every sound is a point. And now design this space in such a way that similar sounds are together, right? Let's say the walking steps is in one place, and whatever sounds which are similar to walking steps, they are also nearby. AC sound is in one place, and whatever sounds are similar to AC sound, they are also in one place. For example, refrigerator, washing machine, fan, ceiling fan, table fan, all kinds of fans, and computer sound, computer noise, all the sounds are somewhere close together, right? So in this way, you define a continuous vector space in which similar sounds are together. And this space is called the embedding space. So you are embedding every sound in a fixed dimensional vector space, right? That's a very convenient approach, because now let's say a new category of sound came. Let's say you designed a new kind of motor which makes some specific kind of sound, and that sound will be lying somewhere in this space, and let's say you have multiple motors of the same type, they all will lie very close to each other and you will get a cluster there, right? So which means you can recognize that sound even without any prior learning on that sound, right? This particular thing is kind of called zero-shot learning or few-shot learning.
So these are static embeddings.
Static embeddings, yes. Static means you just train them once, train the model once, and it gives you the output. You're not kind of dynamically updating your model. So these are static embeddings. Okay, but this problem still remains a lack of established ontology. So many sounds are there. There is no proper study, or I don't know what kind of study can come out which can say these sounds are together or they must be together. So that is not there. Okay, now we studied here the general machine learning approach for sound event detection. So there are different approaches. Like one is supervised learning, which means you know the categories. Let's say I make 10 categories in this room and that's it. And my network will classify every sound into one of these 10 categories. I can make an 11th category saying none of these, right? That is a kind of background category which will put every other sound into that bucket. So that is supervised learning. And this model which directly takes the audio as input and outputs something, maybe category or continuous representation. This is called an acoustic model, right? Now, sometimes this acoustic model can give you directly the class labels, right? Those class labels are represented in a form called event role, and this is how it looks like, right? So this is an acoustic model. Basically, you have some features extracted from the audio. Maybe we have seen some kind of features like filter bank energies and things like that, right? And then you have some machine learning algorithm which will train this acoustic model, and it will give you some output which will be classifying every sound into one of those 10 categories or 11 categories. Then this is how the output will look like. Audio is a continuous stream, continuous one-dimensional signal, and I have, let's say, 3 classes. Then I will tell, okay, now class A has started, class A has ended. Class A could be, let's say, my speech. So I start speaking, spoke, and then I'm silent. Then again I'm speaking, again silent. Speaking, silent, speaking, silent, right? So this is one class. Second class could be, let's say somebody is coughing. Like this kind of, this representation is called the piano roll representation. So on the x-axis you have time, on the y-axis you have different categories, and you are showing how different sounds are evoked in the audio. You can do it in the real time also, right? In real time also you can tell what all events are happening in the room. That's also very impressive. Now tell me, what kind of machine learning problem is this? Classification, regression, classification? What kind of classification? Multi-class or multi-label? How many of you say multi-class? How many of you say multi-label? Multi-class? One person. Okay. Yeah. So what is the requirement for multi-class?
Only one class should be assigned to the.
Yeah. So in this case, you can see, let's say here, how many classes are present? 2 classes. Here, 2 classes. Here, 2 classes. So if you treat it like a multi-class classification problem, then either this or this will be present. Right? So yes, you can treat it as a multi-class problem also, no problem, but then your output will be only one class, not multiple classes together. Okay. So this is generally treated as a multi-label classification, but yeah, some people also simplify the problem saying that okay, only one class is present at a time. That's a simplification, but that is also valid simplification. It's done, means just to simplify the problem. Okay. Then the question is, okay, now different kinds of classification methods are taught here. For example, you may have weak labels or strong labels. So what is you may tell in this audio, speech starts here, ends here, starts here, ends here, starts, ends, coughing starts here, ends here, starts, ends, right? But I may also treat it like another problem where I will just say this entire audio has got some label. So in this audio, there is cough, there is speech. What was this? AC will be throughout. So walking, okay, that's it, footsteps. So three classes are, so I will say three labels are present. You may ask, is there traffic sound present in this audio? You will say no, it is not present. Is there what else? Telephone sound present in this? You will say no, it is not present, right? So then I may ask, okay, in this entire database of audio files, give me only those files where telephone sound is present, or where, oh, in this entire movie, give me only those frames, or let's say you divide the movie into 5-second clips, only give me those clips where shooting is present, like somebody's making gunshots. Give me only that scene. So that is a simpler problem because you don't have to tell start time and end time, you only have to tell whether some event is present or not, right? So you're not labeling every instance as like event present or absent, present, absent, present, absent, but you are labeling the whole audio as event present or absent. This problem is called audio tagging problem, right? Now, what you should think when you are hearing this is, how do you model them probabilistically? What will be your random variable, and how do you, what kind of distribution it follows? So in all of these problems, what are you changing essentially is your probabilistic model, your random variable which you want to model. So let's take the first example. Every instance, let me call it as okay, I think I wanted to discuss something else also. Okay, I'll come back to that later. Okay, let's say here my question is, let's give some representation x n. So what is xn? X is a vector. It is the audio representation. Let's say it is the output of Mel frequency filter bank, right? The Mel scaled spectrogram. What was it called? Mel spectrogram, right? The Mel spectrogram so n is 0, n is 1, 2, 3, 4, etc., etc., etc. This is a signal or time series, and I am mapping this to a representation y of n, where yn is a multi-hot vector. Right? Let's say this is speech, cough, and footsteps. Right? So speech is present, cough is not present, footsteps are not present, speech is present, cough is not present, footsteps are present, speech is absent, cough is present, footsteps are absent, etc., etc. Right? So you are labeling every frame with a multi-label kind of label, multi-hot vector, right? So, how do you define your random variables? Where is my pen? Okay.
So user xn is null frequency output. For xn, that's what you've plotted, right?
Xn is a vector at the nth instance, and this vector represents the Mel frequency spectrum or Mel spectrogram, kind of one single slice. Okay. Now, what are the random variables involved here? You will say, let us treat every yn comma l as a binary random variable, right? Every yn comma l, or let's say y hat n comma l, it follows a basically it is equal to probability of the label at this nth instance. Probability label is equal to 1 at this nth instance, and your label follows a binary distribution, right? I think this one can be ignored just to keep things simpler. Okay. Now this is for the multi-label classification, where you are giving what labels are present and what are the start times and end times of every label, right? But there could be another problem where you are doing only audio tagging. In audio tagging, what are your random variables? So you will not tell yn comma l. What will you tell? Only yl, right? So my yl will say that in this whole audio, speech is present, cough is present, footsteps are also present. There could be more other labels which are absent, right? Traffic, etc. They are absent. So what are my random variables? What are my random variables then? My phi hat L, it is probability of label is equal to 1. For all the labels, label can be basically whatever L labels are there, which means speech, comma, what is that, cough, comma, footstep, so on, right? These are L categories or L labels basically, right? So what is the probability that label is present? That is y hat L. Y hat L is the output of my neural network, right? Or whatever model I'm using. And this L follows again a binary distribution, right? Is that clear? The distinction between two problems and how we mathematically model them, right? Okay. I had left some discussion last time. Because of time, we could not complete it. Let me quickly complete that. I think it will come in the paper also. Somewhere it must be discussed. Okay, so when we have this feature extraction thing, after feature extraction, I can use Mel spectrogram, right? And some people in the past, or most of the works in the past, they used something called MFCC features. How many of you have heard of MFCC features? It's a very common term. MFCC features, no, you've not heard? Okay. It's called Mel frequency Kapstral coefficients. So what are those MFCC features? Okay, did you do that assignment which I gave you? Means it was for your own practice. When I speak A versus E, how do these two sounds differ? Okay. Will you be submitting it? Acha, I told you that the write-up you have to submit in Monday's class. Yes. Yes. Have you done it? Oh, you have not done it yet. Maybe I gave you too long deadline. Okay, then I can't discuss this. I won't discuss this then. Without that, you will not be able to appreciate this concept of MFCC. Okay. Let's do it on after Monday then. We will not do it today. Otherwise, you will not be able to appreciate. Okay, do the assignment then come. Okay, let's do this. Continue with this paper now. You have multi-label classification, and yeah, we discussed about tagging also. Now, context information. What is the meaning of context information? So many times, just by looking one small frame of, let's say, 25 milliseconds, you may not know about the sound, right? If I just give you 25 milliseconds audio, even a human being will find it difficult to tell what exactly is going on. You need to listen to some context. So what generally we use is, okay, let's go back to our figure. Here, these xn are the feature representation, and let's say they are extracted from, okay, let's work with this only. Let's say now you have a model. I'll draw this again. Let's say I have xn, and this is I'm putting them very closely, very tightly, so that you can appreciate what I mean to say. Now you want to estimate y hat n, right? So one possibility could be my model will take only one frame as input, and it gives me y hat n comma l, right? Other possibility could be y to look at only single frame. Let's say this is my n now. I can also look at the context. Right? So I'm not just looking at my nth frame, but also n minus 1, n minus 2, and n plus 1, n plus 2. So I have a kind of bigger context to decide what is my y hat n comma l. So which means my y hat n comma l does not depend only on x hat or x of n, but it also depends on x of n minus 1, n minus 2, n plus 1, n plus 2. Right? So my y hat n comma l is a function of x of, let's say, m, where m is equal to n minus 2, n minus 1, n plus 1, n plus 2. Right? Means just a quick way of writing this. It looks at the context. This kind of model, it is still local. It's local, right? It's local, but it has some context. It looks at the neighbors also, and then predicts something. This is a better way to model things. It has better performance. Let's go back to the paper now. Yeah. Now sometimes there could be short gaps in the event activity. For example, coughing. Do you call, what is the start time and end time? Okay, let me draw it. Say I said, will you call this is the start time and this is the end time, there is a small silence in between, and this is the start time, this is the end time? Will you say it that these are two events, or will you say this is single event with this start time and this end time? What will you say? Okay, single event. Then tell me, let's say if this gap is G, how large can be G before I say that now they are two events, or means after which I say they are two different events, right? How much can I increase G when the single event breaks into two events, right? So something has to be defined, right?
That first signal will be some transient phase, so after some time it will die out. So we can put a threshold. If it dies out of, if it becomes less than that, then from after that we can mark the beginning of.
They could be complete silence, right? Right. Or let's say one baby is clapping. Will you mark every clap as one event, or will you call the whole thing as one clapping? Between every clap there is complete silence, no? So will you call it as two different events or single event? Or means multiple events or single event? That's the question, right? So we define some threshold on this gap, right? Some threshold, maybe 200 milliseconds. If the gap is more than 200 milliseconds, then we call them as two different events. Or in this way, threshold has to be defined. But then who will define threshold, right? So we have to heuristically do something. So this is the practical challenge you will face in this problem. Yeah, depending on the downstream task, you may adjust this threshold or how you want to treat it. So that's what, similarly, short gaps in event activity have to be filled in. And then we discuss, then the topic is machine learning approaches for sound event detection, right? We have to classify every frame or every audio. So we can use machine learning methods like Gaussian mixture models, hidden Markov models for classifying every frame or the audio, right? And I believe in the last class you studied about Gaussian mixture models, right? Now, for hidden Markov model, let's see if we can do it today, or I will share the videos with you so that we can, because this is basic machine learning, I will not spend too much time on this because I kind of assume everybody knows it. Do you know this? Hidden Markov models? Yes? No? Raise your hand, how many of you know hidden Markov models? Okay, only 3 people. Maybe we can then spend some more time on hidden Markov models, no problem. Okay. Okay, and of course, then deep neural networks. You can use deep neural networks to do the classification or whatever, embedding extraction. Yeah, so that's it. This is the machine learning part. Now, you see, I will not spend much time on the machine learning part. I will spend much time on the domain which is surrounding that whole machine learning model. Model anybody can make. It's just one command in Torch or Keras that anybody can do. But how to do it, that's what we are learning in this paper. Okay. Now, the challenge is if you want to train your model, you need data for training. Where will you get data from? Record the data. Oh, there are public data sets also, but okay, assume that you are the one who is doing it for the first time, or you're doing it for a very different kind of application and there are no existing data sets, right? Or how did the people who studied this problem, how did they solve it? So what did they think when they made a plan to do the data collection? So one thing which we should be very conscious about is acoustic variability, which means I should collect my data in such a way that I am collecting sufficient variability of how the data may look like during the deployment time, right? For example, if I'm deploying it within the classroom, I have to make sure that I cover all possible classrooms where this model can be deployed. Let's say I'm planning only to deploy it in Indian settings, right? In Indian settings, then what kind of sounds can be present? To kind of try to cover all of them. So for example, in US or UK, you have fire alarms. But in India, we hardly have any fire alarms. So you may not collect data about fire alarms in Indian settings. But in US, they definitely have to collect fire alarms also. Otherwise, it won't work there. Right? So data collection is a task which you have to design very carefully. Then data labeling also is a task which has to be done very carefully. Okay, I have myself worked on this problem of data collection, data labeling, data preparation, and then this was the kind of part which I was kind of managing. There was a team of data annotators, there was a team of data collection people, but then how do I make the whole process, whole pipeline for them which they can follow? And it's a real difficult task. How do you collect data? So do you collect data from open environments, or do you simulate the data computationally, or do you simulate the data physically? Let's say if you want to
By simulate, you mean synthetic generation?
synthetic generation. Let's say you want to collect data of how AC looks like. Turn on an AC, record it. How do you want to collect data about how cuffing is like? What will you do? You have to cuff, but how much can you cuff? So call people and ask them to cuff. Or we go to a hospital and collect data about cuffing. Right? It's a real task, real challenge. And now let's say you want to collect data about gunshots. What will you do? Sorry. Yeah. How will you do gunshot data collection? One way could be, how many of you are in NCC? How many of you have done NCC before? Do you hear gunshots in NCC? How? You go to shooting range, right?
Yeah.
They take you to shooting range. Go to shooting range and record the data. You have to think, how do you collect the data? Or you may collect data from movies. In movies, there are so many gunshots. Or what else can you do? Video clips means, yeah, movies or video clips. Yes. Games, yeah, synthetic audio, like from
Don't you have
games.
to worry about the authenticity of the gunshot sound in movies and video games?
Yeah, yes. So if you're deploying it for movies only, then you have to worry about movie sounds or the sounds which are present in movies. But if you're deploying it in real crime settings, let's say police wants to deploy such sensors all over the city that wherever something happens, police will know it immediately. Then you have to consider those kind of acoustic sounds, right? Yeah. So these are some possibilities. Yeah. So all these things they come under data collection, and some environmental factors can be simulated. For example, you collect the clean gunshots from your shooting range, and then let's say you add some traffic noise in the background to simulate, okay, this is a violence activity happening in the public roads or something, right? Okay. So this is a challenge. Then comes annotation. Now there could be, how will you annotate the data? You have gunshots, how will you annotate them? One option could be take pen and pencil and record the audio, note down, oh, it starts at 5 milliseconds, or let's say 10 seconds, it ends at 13 seconds. Then again it starts at 20 seconds and ends at 22 seconds. Or you write in a CSV file or Excel sheet you write. It's very tedious. Or people have come up with now tools, you look at the audio signal and then just with a click of a mouse you can click, okay, now it has started, now it has ended, and then write down in between whatever is the category or maybe some ways. So this is, there are tools to do the labeling. But then, even then, it's a very tedious task, listening to the entire audio and then labeling. So there are two kinds of labeling which is done. One is called strong labeling, where you actually mark every start time and end time. That is strong labeling. But there could also be weak labeling, where you just tag the audio. Okay, this audio has got gunshots, wherever it is, but it is there somewhere. Or this audio has got traffic noise. It may be all through or it may be in some location. You don't worry about that. Right? That is called weak labeling. Just tags are given. That is much faster, right? It is much faster, and nobody will complain. Oh, you did not mark. You missed it by 10 milliseconds or something. Nobody will complain like that.
So, what is the threshold? If the amplitude crosses the threshold, so as you're automated, right? Because what we're recording is like a single class sound. For gunshot or traffic, we only like traffic noise in the entire clip. So I can't just automate it by saying that when it crosses the threshold, we have the start and end.
Good question. Now let's say you have traffic noise. Let's say you have recorded an audio where there is a air conditioning sound in the background and I'm speaking. Where will you put the threshold now?
But what we tend to do is we tend to isolate each sound, right? Like audio is only audio sounds. In the training data at least. Like when you're speaking, we just want that sound in the entire clip, right? Or we don't want the ACR part.
But let's say when you recorded it, there are other sounds also present.
In that clip.
Yeah.
And
And sometimes the sounds themselves could be very feeble. Let's say, I will tell you one use case. We were working on bird sounds. And sometimes the birds, they chirp very softly. Then you will simply miss it with a threshold, right? Sumit was working on that project. What can you do there? Okay. So yeah, so basically strong labeling is challenging. Weak labeling is simpler.
So can you do first unsupervised clustering and then label?
Yeah, something similar we did. First try to do unsupervised way and then use some little bit supervision. It's called semi-supervised approach. That is a good strategy. Yes, thank you. What's your name? Akshat. Okay, good. Yeah, so that is strong labels and weak labels. Now imagine that you are given only the weak labels. How will you learn from weak labels? That is another challenge. Oh, I think that will be discussed later. Okay. Another approach for labeling is, now who will label? Okay, you defined a strategy. Okay, I want weak labels or strong labels, and I will be using this tool. Okay, but who will actually do that labeling? So either hire people, train them, get it done, or do crowdsourcing. What is the meaning of crowdsourcing? You put it on some website, and there are people who have developed such websites where you define your task, you define your tools, and then this will be there on their platform, and then people will come, like just people from all over the world, they can just join that platform and they will come to your task and they will just listen to it and do it casually, and based on how many they are doing, they will get paid. So they will take their money and they will leave. So it's called crowdsourcing, where you don't know who are the annotators, they are kind of lay people around, and they are just coming and they are learning a little bit about the task. You can give them a little bit training, not much, but little bit, and then they will do some task and they will leave. You may have to define measures. How do you quantify their performance? Somebody may be just casually marking something, generating very bad labels, or somebody may be doing it very seriously. And how do you distinguish these two kind of people? Like, because the bad labels will simply be useless, but good labels will be should be more valuable. So there are methods for crowdsourcing, and I discussed some of these methods in the MLSP course, where you use metrics. Let's say you have 10 people who have annotated the data, and then you can do a voting. Let's say I'm doing audio tagging, let's say, is speech present here or not? 10 people have said, just take the majority vote. Okay, 8 people said yes, it is present, so let us take it as present, right? And then there could also, you could identify who are the bad annotators. Let's say if somebody is consistently marking wrong things, you may either stop him from coming or pay him very little or something. So, and then you have, yeah, that's what crowded annotations may be referred to as noisy data. So, because labels could be incorrectly attributed or missing altogether. So therefore you have to do some kind of curation for improving its quality. There are methods to do that. Simple statistics, but very useful. Okay. Then we go to next part, which is signal processing methods for sound event detection. Now, to generate more data, you can use data augmentation. How? Let's say you have one audio file where speech is present, one audio file where AC is present. You mix both of them. You got a new speech file which has both speech and AC present, right? Or you could have, let's say, one audio file where speech is present. Now you use some signal processing method so that speech is still there, but its quality changes. For example, what can you do? I think if you have worked with Librosa, you should be able to answer this question. Or Pratt. Huh? One possibility could be just add some noise. Not AC noise, but Gaussian noise. Or add some general noise from environment or something. Or some class which is not present in your target classes. Let's say train noise. But train is very sharp. Maybe something milder. Maybe in a children park, children are playing. Just add that kind of noise. That is one kind of augmentation. But then you could use some systematic signal processing methods. For example, pitch shifting. You can shift the pitch. Or time elongation or time stretching. You just do time stretching or time compression. Simple signal processing methods. But using them you can generate more data. Right? These are all the methods of data augmentation.
Time stretching, compression different from pitch.
Good question. Let me say this. What is the difference? When I say let me say this and let me say this, both have same pitch, but my speaking rate is different. Probably you are thinking in terms of stretching the waveform. Yeah, if you stretch the waveform, then what will happen? Your pitch will decrease, right? Your time will increase and pitch will decrease because sinusoid will be like it will cover same area, same length in longer cycle. So pitch has gone down, right? But let's say I'm not stretching my waveform. I'm repeating my waveform. Let's say I maintain this frequency only, but now instead of one cycle, I introduce 1.5 cycle or 2 cycles. Then it is stretching as well as maintaining the pitch. So that is what is done in Librosa or other standard libraries. And likewise, you want to change the pitch. Don't change time, just change the pitch. Let's say you have one cycle of some frequency. You want to increase the frequency. Don't change the endpoints. Only change the frequency of sinusoid. Then it may have more cycles or less cycles. Right. So this method is called in literature phase synchronous overlap add method. It's a popular method for time stretching or pitch shifting. Phase synchronous overlap add method. I will not discuss the details of that method, but you can read about it. It's very simple. Just you kind of because you have to make sure that you don't break the phase. For example, now you change the frequency and your endpoint was earlier 0, but now endpoint becomes 1. And the next frame, it starts at 0. Suddenly there will be a jump, right? It's not synchronized. This cycle is ending at 1 and then this cycle is suddenly starting at 0. Then that is not a desirable state. You want to make, okay, it should end at 0 only. So that's why you have to take care of this problem. It's called phase synchronous overlap add method. Okay. Yeah, so this figure shows you strong labels versus weak labels. Right? I think it's very clear. Data augmentation you can read on your own. It's very simple. Okay. Feature representation. Yeah, okay. Here we are. In feature representation, we discussed about MEL spectrograms, right? This was a MEL scale. And we use triangular filters on the MEL scale, and this is all we discussed. Now, there's a discussion about MFCC features. These features are very popular. They were very popular earlier, and today also like people use. But okay, people may use MEL spectrogram directly also, because deep learning it can learn on it can learn very efficiently from the raw means a feature which is closer to the raw form, a less processed feature. But MFCC, what it does is it applies discrete cosine transform on the MEL frequency or MEL spectrogram. You apply discrete cosine transform on MEL spectrogram. Okay, I told you this, but the question is, why to apply DCT? Why not something else, or why to apply anything at all? So this you will not be able to appreciate or understand properly unless you do that assignment which I gave you. If you do that assignment, then you will be able to appreciate why DCT and nothing else. Right? Let's say tomorrow you work on some new kind of signals. Maybe you are in some company where they are doing some other kind of signal processing. Then they will ask you, can you design some new feature representation for us? And you will say, I don't know, I only know MFCC, they do MEL spectrogram and then DCT on top of it. But they will say, no, this is not speech, this is a new kind of signal. Then how will you do that? So unless you understand these principles, that why DCT is applied there, why MEL frequency is used, not the linear frequency, right? What was the principle? Why did you use MEL frequency? To make the sensitivity uniform, right? Okay. So remember these principles, they are not there in the books, but I'm telling from my experience. So, but that's how you do science. You need, maybe they are in the very old papers written on when these things were invented, but now since these things have become so much regular thing that nobody even thinks that why we are doing it. Okay. Then there is something called constant Q transforms, which is very similar to MEL spectrogram. Yeah. Now machine learning for sound event detection. What do we use? What can you use? You can use convolutional neural networks. You can also use recurrent neural networks. Have we studied recurrent neural networks in this class? No. We have not studied, right? Maybe our next goal will be to study recurrent neural networks. We will do that. Then people have combined convolutional as well as recurrent together to learn the signals. I will come back to this after we discuss recurrent neural networks, okay? Now, every machine learning model has got some hyperparameters also. How do you select hyperparameters? Have we discussed this in this course? Grid search and random search? No? Okay. Okay, we will discuss it. We'll discuss it a little later. Then there are methods like transfer learning. Let's say I ask you, design a system which can detect when I'm speaking, or let's say detect all the sounds present in this room. What will you do? You can collect data, train your model from scratch, right? That's one way. But then you have limited data only, very limited data. Like my speech, how much can you have? Maybe 1 hour, 2 hours. That's it. And let's say a new speaker comes. How much data can you collect from that new speaker, right? And then this AC, how much can you collect? So what people use is they take a model which is pre-trained on lots of other sounds. Could be AC also, could be speech also, but from other speakers. And then they bring that model and initializing from that model, they train the model on the new categories like my speech and AC, let's say. This is called transfer learning, which means you are bringing a model from pre-trained on some other similar tasks and then transferring it to this particular task. Right? This is called transfer learning. Or you can also call it adaptation. You're adapting your model to this new task. And we discussed about embeddings, we discussed about Yeah. Now there is something called multiple instance learning. Now the problem which we just now saw here, when you have weak labels, let's say this is some audio file, some X. For this, I only tell you the weak label. So let's say speech. If I say speech is present, does it mean only speech is present? No. It is weak label, which means there could be speech in some of the frames. Let's say there are multiple frames here. So some of the frames will have speech, some of the frames will also not have speech. They may have other things but not speech. So which means you know that in this instance you will have some labels have speech, some labels don't have speech, which means it is a mixture of positive and negative. There are positive instances where speech is present, but there could also be instances where speech is absent. So which means this is a bag of positive and negative samples or instances. So each of this frame can be called as an instance. There are positive and negative both kind of instances present. And now I give you another X where you say speech is absent. What can you say about these instances? These instances, are they positive or are they negative or are they both? So all of them are negative for sure. So this is your machine learning problem now. You want to do a classification, binary classification, speech is present or absent, but the data which you have data samples which is a mixture of positive and negative, and you only know that somewhere in this data you have positives also, and another data samples where you have only negatives, that you know for sure that there is no positive sample here, right? The question is, how will you do machine learning now? How will you learn? How will you design your loss function? How will you design your model? How will you do that? So one approach is you estimate y hat. Here label is only one label. Okay, let's say even if there are multiple labels also. So you estimate y hat n comma l, and then, but what is your target here? You don't have any target, right?
We don't have the y n comma l labels. We just have the weak labels, right?
This is y hat.
Yeah.
Estimated from the model. Model has some output. In the beginning, it is just random weights. Let's say some random outputs, but we have y hat n comma l. We don't have y n comma l. We don't have. Yes. So then, how do we train it? What is the loss function then? What should be my loss function? What I have is only YL. I have only YL. YL could be either 1 or 0, the targets.
Could we think that we want to make the label 1 sound and label 0 sounds as different as possible?
You have read it somewhere.
Very different, then the cost would be less.
Yeah, but then how in this entire thing, where is the positive, where is the negative? We don't know.
As overall, if we can define some parameter, then we can calculate that how differently one label sound and 0 label sound are different. So as different.
No, let's say like which one will you take as positive? Because here, okay, yeah, sure, negatives are there, but which one is positive, which can move away? You don't know.
Let's say the estimated probability is when that estimated probability is above some threshold, then we consider it a positive instance.
But in the beginning, it is totally random.
Okay.
So this is a serious problem, and that's why there is an algorithm or there is a method called multi-instance learning. So what is done is you apply some kind of a pooling here. This pooling is done across n. Let's say you got some, this gave you some, this will give you something called, let's say, maybe y1 hat L. This one you can compare with this using whatever categorical cross entropy or whatever, or binary cross entropy, etc. This is one method, right, where you pool it. Pooling, what is the meaning of pooling? Let's say I take max. Right? In the beginning it will be random, but over a period of time it will learn. At least it will learn for sure that these are the negative samples. So these should be away from YL, or the basically this should definitely be 0, right? And then some of these samples, let's say, I will just graphically try to show it. So in the feature space, I'm not talking about embedding space, in the feature space, let's say these are my negative samples, and somewhere are my positive samples also, right? Then I know for sure at least that these samples are the negative samples. So I will define my classifier, let's say, in this way. This is negative class, this is the positive class, right? Because this has to be 0, so my classifier will be something like this. But then here something has to be positive, so it will try to find a place where somehow wherever these positives are, they come to the positive side, so that at least when we do pooling, something is there positive, right? So which means that this thing will turn and it will become something like this. And as the training proceeds, it will turn more and more, and it will learn this boundary. Something of this sort.
Okay, so even if there are only a few positives, since we want the label to be 1, the pooling should behave in a way that even a few positives can make the whole thing.
Yeah, you can take max pooling probably. Just focus on those instances which are possibly positive, right? And you know that there must be some instance which has to be positive, so it will find in the feature space where should that positive be, right? Read the paper.
Isn't this similar to what k-means clustering also does?
K-means clustering. Okay. Did you do k-means clustering in the last class? Okay. Yeah. K-means clustering. There you know exactly the centroids, and your data is pulling the centroids. Yeah. I don't know if you can. Maybe you can relate it with k-means clustering somehow. Maybe. Yeah, good connection, but I have not thought about that. You can think about it.
Sir, if my labels are given on the whole instance, so why do we predict on each time step? Like my label is given for whole clip, and so why are we predicting by n comma n?
Yeah, that is also one valid method, one valid question, that your output should not be y hat n comma l, but simply y hat l. Simply y hat l. You make a neural network in such a way that the output is simply y hat l, and then you can compare with yl directly. Yeah. But to reach to that y hat l also, you have to do some kind of pooling intrinsically by the model. Like either you use a dense layer which will pool everything together, or something of that sort, right? So yeah. So then here you are intrinsically doing some pooling. Yeah, that's also a valid approach. So one thing which works very well, state of the art, is called attention-based neural networks. What they do is they will weight all the instances, that which instance should be given higher weight in the pooling. So it's like a soft weighted pooling. Right? It's a pooling, but it is a kind of weighted pooling. And these weights are also predicted by the network. By looking at the instances, the weights are also predicted by the network. But the constraint is that these weights, all instances cannot have high weight. It's like a softmax thing, where our weights will be concentrated to only certain instances or certain number of instances. That is called attention-based neural network. So I think we can have one class on attention-based neural networks also. It's a really popular these days. All these ChatGPT, they use attention neural networks. They use something called transformers, and transformers are basically attention-based neural networks. So we can discuss that sometime. Remind me, sometimes later in the course we will discuss attention-based neural networks. But of course, you are welcome to read about it on your own. Now there are some open public source datasets like AudioSet, which have lots and lots of audio, and you can use it for training your network. Then there are methods like student-teacher methods, knowledge distillation methods, which are useful to compress the models. So imagine you have some pre-trained model. Okay, how many of you know about VGG? So it's written here, VGG. So VGG is a neural network trained on so many millions of images, which are labeled images. That this is a face, this is a car, this is a sparrow or something, right? So you have some data set which has got millions of images, and VGG network is a convolutional network which is trained on those images to do the classification. It's very deep, and you can't afford to train it on at your home. It's very deep network, and it requires lots of data, lots of GPU resources to train it. But then the advantage is this network is available, trained network is available for you to use. So what people do is they just apply this network and extract some features. And these features are sufficiently discriminating between different classes. Remember that embedding thing I discussed with you? That different classes lie in different pockets of this embedding space. Right? So that's what VGG network does. It will give you an embedding where things are pretty well separated, right? And then you apply your another classifier, a small classifier on top of it, and you get your task done. Train that model because it has less number of parameters. It can be trained very efficiently, right? So something similar is also done in audio sound event detection. That you take some model like SoundNet or L3Net, and recently there is a model called PANS model, which has been trained on really massive amount of data. Just like you have ChatGPT, you cannot afford to make it at your home. It's like, but you can use it. The pre-trained model is available. Now you can use it for different tasks, whichever you want to do. Likewise, you have PANS model, which is pre-trained on large amounts of audio data. And you can just take that model and use it for basically use it for feature extraction, and those embeddings can be directly fed into another neural network, small neural network, which you can train to do the required task. Right. Now the thing is, this overall combination, it becomes a huge model, because PANS model is a huge model, and you have a little small network at the end, but the whole overall combination becomes a very huge model. Now it's very unreasonable to say that let me deploy it on a mobile phone, or let me deploy it on a small device, or even to run it on a computer. Let's say I want to run it on my PC or my laptop. That becomes a very challenging thing. So what people do is they use something called teacher-student approach. Okay, I'm not going too deep or into the details of these methods because I think they are so easy. We don't have to spend classes after classes discussing them. They're very easy methods, and you can just read about them. There are references given, and even the paragraph is sufficient to help you understand what they do. And in machine learning, the technology is changing so fast that there is no point in investing in one kind of current method, because at the very next year probably that method will be outdated. So what you should actually try to learn are the principles which are used to build all these methods, right? For example, CNN is there. Why CNN works? Because it takes care of
Side other data apart like you were telling
what is the term we used? Translational invariance. Translational invariance or translational symmetry. That is the property which CNN uses. If you understand this, you don't have to worry about all the terminology that CNN people use. Similarly, attention also, if you understand the concept, you can just, for example, GPT, it uses attention in a certain way. You have some other model, it uses attention in some other way. But if you understand attention, then understanding those models is so easy. Okay, so now what is teacher-student model? So you have, you take this large model, call it as the teacher. Now you build a small model which you want to deploy on your machine, call it as a student. And you have lots of, let's say, unlabeled data. Pass that unlabeled data through the teacher. Teacher will give some output. But that, for the student, that output is the target. Input is there, this is the target. Now this serves as the training data for the student. So student does not worry about the label data because the teacher will give it the labels. It only learns from the teacher. So what are the advantages of this approach? One advantage is that
You can use supervised learning instead of unsupervised learning methods.
yes, the student can simply learn from supervised method, supervised training. What else? Even when you have limited data in your domain, or even when you have sufficient data in your domain, but you don't have to employ so many annotators to annotate the data, because teacher will do the annotation for you. And finally, the student is a small model. You can deploy it on your phone, deploy it in the classroom, on your simple computer. It's very easy to work with it. Another advantage which it has, how do we take care of outliers? Sometimes not outliers, but let's say difficult cases. For example, if there is some audio which is very difficult to classify, but the annotator may label it as a particular class, but actually it is in the gray region and annotations are not very perfect. How teacher will learn, because teacher has seen such a large world, from its experience it knows that this is not actually, the label is wrong basically. The teacher knows of the label, that label is not wrong, not correct, or the label is not appropriate. But for the student, because now it is getting the label from teacher, what is teacher's outputs? Teacher's output, teacher will say it is a gray zone, so teacher will be giving, let's say, 0.5 weight for speech, 0.5 weight for some other category, right? And the student will also learn, okay, this is a gray region, and I should also assign 0.5 for this, 0.5 for this. In this way, the student, the cognitive load on the student is not much. Teacher has simplified things, and student can simply learn from the teacher's experience without getting confused because of these gray area kind of samples, right? So in simple language, if I have to say, that student will say, if teacher cannot solve, why should I worry solving it, right? So that is the advantage. So your student model, even if it is a small model, very lightweight model, it can do the task very efficiently, because it says, if teacher is unable to do it, why should I do it? So let me focus on those things where teacher is confident.
Is this an extension of transfer learning, or is it a separate model altogether?
It is called knowledge distillation. This is not transfer learning, because you are not training on one domain and testing on another domain. Okay. For the teacher, you can say it is transfer learning. Teacher is transferred from some domain to some domain, let's say, or may not be transferred also, whatever. But for the student, it is Certainly not transfer learning. For student, it is only learning in a supervised way from teacher's outputs.
That's a totally different model that you create for the student.
Yes, student is a totally different model. Because our goal is to make a compressed, lightweight model. It's very useful, especially when you work on edge devices, means like mobile phones, etc., where you don't have that much compute power, but I want to make a model really good. Then this knowledge distillation helps us. So you can see here, it can compress a large model, that is the teacher, by teaching a smaller one, the student, to mimic the behavior of teacher by replicating its outputs. Yeah. So I think if you read the paragraphs, whatever I explained now, it will make complete sense to you. And then you can read the reference number 38. You can read further details if you want to use it. Next comes evaluation. How do we evaluate our model? This is a very good question. I will show it with the help of, okay, let's take the audio tagging task. Whether speech is present or not. How will you evaluate? We have read some metrics. What are those? Accuracy, F1 score, which means precision and recall. Confusion matrix, all those things you can use, all you are aware of. But let's say if you are doing sound event detection, which means you are also detecting start times and end times. Now how will you evaluate?
How much deviation from that to like?
How do you define the deviation then?
Like we can consider something like the actual start time and the start time predicted with by our model, and we
Okay,
can
good.
calculate some
That is this.
average time.
That is this model. It's called event-based evaluation. Let's say reference is the ground truth, the orange one. What I predicted, let's say, maybe I predicted this way, the green one. It starts here, it ends here. Now you can see that there is a little bit mismatch. I define some tolerance. Okay, I can allow 200 milliseconds of mismatch in either direction. Not more than that. If there is more mismatch, like this case, if you predict this, I will mark it as incorrect because you did not fall into the window of 200 milliseconds. Right? This is what you are suggesting, Akshat. Who suggested this?
So I'm not suggesting this. I'm saying like for classification we have our cross entropy loss, and for shift we have a loss that is like something like mean square error. Like you calculate the difference between the predicted onset
Oh,
time and
so you are saying don't mark it as correct or incorrect, but just measure the mean squared error between start time and end times.
start time and end time. And for classification you can have another loss and you can use some of both losses.
Okay. Yeah, that could also be good. Here, just it is binarizing it, either correct or incorrect. You are giving a soft. Yeah, both are correct. Okay. So this is a standard way which is used in international kind of standards. This is one way. Any other method? Okay. Anybody can tell me limitation of this method? How many events you make out of it? Let's say the ground truth says, now ground truth is made by human beings. Every human being is different and they may have some different understanding. Somebody may mark it as 2 events, somebody may mark it as 1 event. You can do some pre-processing saying that, okay, if the gap is less than something, then merge the 2 events or something. You can make those adjustments. But that problem still remains that maybe your reference has got 2 events and you predict a single event. Or your reference has single event, you predicted 2 events. So in that case, you will get 0 marks, right? And also, okay, so for this, there is another method invented. What is that? This one. So you divide your timeline into a grid, like a coarse grid, maybe 200 milliseconds gap, right? And then if an event is present, let's say you define a tolerance, maybe 10 milliseconds or something. If it is present for more than 10 milliseconds, then you say this entire grid has this event. Like all these have the event. And here, this event is only in 2 grids, so you just mark them. This is only 1 grid, 3 grids, 3 grids. This is my ground truth. And likewise you do for the system output or the prediction, right?
Why are there two axes in the output?
Pardon? There are?
Why is this a square grid and not something linear?
Yeah, it is actually linear, but these are just multiple instances, multiple examples.
Okay, okay.
Multiple examples. Let's say this is my reference, this is my output. Or you can also see it as different events. This is a speech, curve. Both are correct understandings. Okay. So now you got this kind of binarized grid. Now you can find out simply true positive, true negative, false positive, false negative, and do your precision recall, F1 metric, etc. Right? That's how, these are the two different methods, so which we now discussed. This method is called segment-based event activity detection. So why it is called segment? Because you are making this grid, these segments, beforehand only. So whether now, let's say if you say, if they come in these two regions, even if there is a gap between them, here they will be just combined together. Means I don't care how much is the gap. That's why it is called segment-based score, and this is the event-based score, where you actually every event is a separate entity. Both of them will be able to kind of give you some, means both of them are reasonable, like nothing is unreasonable here. Both of them are reasonable. Okay. Yeah. So both of these are used for international competitions and all. By the way, there is an international competition around this event which happens every year. It's called DK's Challenge. Many people participate in that, and you can also participate if you want to next year. I don't know when is their deadline. Sometime maybe in March or April, huh? Okay. I don't know. We have to check. There is a web page, DK's Challenge. They have a very good website. They have been doing it for more than 10 years now. Yeah. And these are the people, the authors of this paper are, these are the people who were the beginning kind of people who started the DK's Challenge, like Mark Plumley and Thomas Virtanen. Yeah. Okay. Oh, by the way, Tony gave a talk here last week. Last week, right? Last week he gave a talk in ITK, online talk. I forgot to share the invite with you, but we have recorded it. I can share the recordings. So yeah, actually, I just forgot to forward it on the class. Okay, so that's it. This is how you evaluate your model. What else? Then, okay, research problems. What are the research problems? It is still a research problem. One is adaptation, as I told you that I want to deploy something for this classroom. Or let's say you are, some company comes to you, they say, oh, we have got so many machines in our factory and we want to make a monitoring system which will detect which machines are developing some kind of fault, so that we can take an early action, and before the machine actually breaks, we can correct that. I mean, let's say some gear has come out or something, the machine will make some strange kind of sound, but it will still be running. But then after some time, other gears will also start breaking because they are now hitting each other in a very bad way, and everything will eventually break. So can we do an early intervention that, okay, that as soon as the sound changes, immediately an engineer goes and sees what has gone wrong, and immediately some action can be taken before the whole thing collapses. So this, let's say somebody invites you, somebody calls you, can you make a system for me? You can say, okay, let me take some pre-trained model and then adapt it to this problem, right? Adaptation. Or maybe you made a one model for one factory, then they say, oh, we have another factory there. There the machines are very similar, but we bought them. These are new machines, so their sound is slightly different. Now, how will you train the entire model again? The other method is just adapt it with a little data, fine tune it or adapt it to the new problem. And then multiple microphones. Let's say you have multiple microphones and you are learning zero-shot learning, which means you have you can read more about these. Zero-shot learning means you don't have any data, but still you want to detect the class. So, for example, I just ask you, does this event sound like speech, or something of that sort? Or I may ask you, this sound, it sounds like a clapping sound because there is a periodicity and the periodic bursts. Okay, let's take this example. Describe it in terms of other sounds you have heard. One is the thing I told you. It's like clapping. There are intermittent bursts or periodic bursts. What else?
Someone
Huh?
running with heel shoes running back.
Yeah. It sounds something like heels are
A marching sound.
striking on the ground. Yeah. So I just told you some attributes about this new sound, but I never gave you the actual audio sample of this sound. So can your model still predict or detect this sound? So that is the problem of zero-shot learning. So it uses auxiliary information about the new classes, such as their textual descriptions, in order to obtain an acoustic model. Right. So it's a research problem, and or if I just ask you, let's say you are making a documentary. How many of you make here documentaries for some clubs or something? Some video editing somebody has done? Nobody? Okay, when you make a documentary, or let's say you are doing some video editing, you may need some sounds to fill the space. Let's say you're making a documentary of, let's say, some sports. You say, I want a sound which is something like upbeat sound, and it's like exciting, and let's say India has won the World Cup, and there are. So can I find that? So you write a textual description, and the model will fetch you that kind of sound. Right?
Sound generation.
Not generation, but search. You have a big data set, and just to pick the sound. Let's say I can simply say, okay, fetch me a music sound. It will fetch all the music files, but then which one is appropriate, I may not know. Or you can say, fetch me a sound where soldiers are marching. That label is there, it can fetch. But let's say you give very, very descriptive input. That I want a sound which is music, but it is upbeat, and it is this and that and that. How will it fetch such a sound? So this is a research problem, zero-shot learning. Okay, in this way.
And this kind of problem also involves language processing.
It may have language processing also. You can simplify it by saying that while training itself, you can define some of those attributes. That, okay, is it periodic bursts? It is this, and all those attributes you define during training itself, and then while querying, you can simply specify those attributes. I want this attributes. And then it will search. Yeah, so basically various ways to handle this problem. But yeah, NLP is also useful. I'm sorry I went over time, but I hope this was interesting enough for you. We did less mathematics, but more of understanding the problems.